New Zealand's kiwifruit industry has seen massive growth in recent years, increasing 36% from $1.86 billion in 2018 to $2.53 billion in 2020. Despite this, the kiwifruit industry has a large shortage of workers, short 1,200 workers in 2018. With the recent COVID-19 pandemic, this has likely worsened. Kiwifruit orchards require regular pruning. This is to remove excess vegetation that may be causing inefficiencies in the plant's growth. Workers are responsible for this pruning, but require knowledge and information about the orchard to make these decisions. We need to make sure that the workers have access to this information in a clear and concise way. The aim of this project is to measure the canopy density, or depth of the kiwifruit vine canopy, and potentially the leaf area index, or percentage cover of vegetation within the canopy. These measurements would be taken from an autonomous or towed vehicle, which would maneuver through the orchard. This data may then be centrifuged with GPS measurements to record their locations within the orchard. One requirement of the project is that the proposed method is low cost. This ensures the final product is financially viable for orchard operators. Several methods were researched, including LiDAR, machine vision, and ultrasonic, but ultimately radar was deemed the best fit to capture canopy depth measurements. Data from this radar would be sent to a connected computer, which would then be transmitted wirelessly to a remote computer. From here, the data may then be presented to an orchard operator or worker using a graphical interface. Presently, canopy depth and leaf area index measurements are measured manually or by using handheld tools. This is time-consuming and requires operator training and skill. Autonomous or towed measurements would allow for much more efficiency in collecting this data. In recent years, the use of autonomous cars or drones for data collection has become more popular, especially with the reduction in cost of advanced sensors such as radar, as it sees more use in the automotive sector. The solution proposed is also scalable, allowing the fusing of more sensors if necessary. The proposed design consists of an omnipresence 24 GHz frequency modulator continuous wave radar, which offloads measurements via USB serial to a Raspberry Pi 3B Plus computer. These measurements are then transmitted via Wi-Fi to robot operating system, or a remote computer, where they may be analyzed. Video shown demonstrates the output of the radar, with peaks in the output moving to higher index values as the object is moved further from the radar, and to lower values as it is brought back closer. To test the radar, two tests were conducted. The radar was first placed on a level surface. Bird netting was then suspended 62 centimeters above the radar. Leaves were added to the netting in 100-gram increments, with measurements taken at each increment. This was repeated 10 times. This test was then repeated at a height of 95 centimeters, with leaves added in 250-gram increments. Each measurement created a CSV file consisting of 512 values, each value representing the amplitude of frequency components of the signal, which could then be converted to range data. The plot on the left shows an example of this data, with large peaks at lower index values representing objects closer to the radar. From the plotted range data, no clear patterns were visible in the shape of the plots. The 512 output values for each measurement were then summed and plotted as leaf weight increased. From the plots, an overall increasing trend is visible. Although these results are hopeful, variables such as electromagnetic interference, temperature, wind, or moisture may have had an effect. To ensure that this trend is not the result of random variables or their environment, the radar should be tested within a real orchard. Plans for this testing were made, but were unfortunately cancelled due to the ongoing pandemic restrictions. Future work that may be undertaken to further the project includes the testing of the radar within a real kiwifruit orchard, to better replicate the environment and variables that may be present. Leaf area index measurements may also be recorded with a camera to determine if a correlation is present with the radar measurements. The radar will also need to be tested while mounted to the vehicle and moving to determine what effect this may have and to determine a suitable speed. Sensor fusion with a GPS module will also need to be implemented to ensure that the accurate locations of measurements is recorded. Finally, the output data will need to be processed by robot operating system and output to a graphical interface that may be presented to an orchard operator. This involves connecting robot operating system to the wireless system. Thank you.